problem there. Okay, so prior to this, we studied magnetism, and what we learned is that magnetism is an emergent phenomenon because of electron correlations. Electrons interact with each other. There's a repulsive interaction, and then there is this Pauli exclusion principle, which together give rise to some effective spin-spin coupling, which is responsible for various magnetic orders that we learned about. And we spent some time understanding microscopic origins, some mechanisms of emergence of this spin-spin, what we called exchange interactions. So superconductivity is another such phenomenon which appears, which is an emergent phenomenon due to electron correlations. And I use the term correlation in a very general sense, in the sense that electron interactions and Pauli exclusion principle. So we will try to understand how or what sort of electron interactions give rise to superconductivity. Okay. Now, there are different types of superconductors. Before that, I mean, this topic of superconductivity is huge. I mean, it's more than a century old. So many people have spent so much time and resources studying superconductivity in all kinds of materials, or at least different kinds of materials. And of course, it is not possible to do justice to this in a span of 2-3 lectures. So we'll just try to understand the basics of it. Now, talking of the phenomenon of superconductivity, there are different types of superconductors or different types of superconductivity that appears in different types of materials. Most of our discussion will be focused on what one would like to call conventional or classic, and finally we'll get to the term Bcs superconductors. So this kind of superconductivity appears in various metals and some compounds also. Niobium diselenide is one of the very well studied this conventional superconductors. Now, what characterize these materials or this type of superconductivity is that they have usually low transition temperatures. By low, one means it can go from half a Kelvin to 10 Kelvin or maybe 20 Kelvin and so on. And in these types of superconductors, the essential mechanism involves electron-phonon coupling. So the interactions, the phonon-mediated interaction between electrons is responsible for superconductivity in this kind of materials. So when we studied magnetism, at least to the extent we discussed magnetism, and which is a good sort of level for a wide class of materials actually, the phonon was completely out of the picture. We didn't need to worry about phonons and lattice vibrations and so on. Even without those, many essential features of magnetism could be understood and explained at some level. Now, in these type of superconductors, phonons play an essential role. So without phonons, there would be no superconductivity in these materials, at least. So this mechanism of phonon-mediated superconductivity, the microscopic picture was given by, so the superconductivity, we'll come to this, was discovered in 1911 by Kamerlingh-Onnes, and the full theory or the microscopic theory had to wait for the 46 years. So it was 1957 that Bardeen, Cooper, and Schrieffer came up with their microscopic theory, and which we will study at some level, which explained many of the observed features of this superconductivity. superconductivity. Now, so these are conventional superconductors, and as I said, we will spend most of the time trying to understand these. But then the discussion would remain incomplete in today's time without some reference to high temperature superconductors. Now, high temperature, as the term suggests, these superconductors have high transition temperatures, higher than the conventional ones, above 30 Kelvin to all the way to something close to 200 Kelvin. And the first class of compounds in which this type of superconductivity was observed was copper oxide. So there's this family of copper oxide compounds. The first one to be studied, and in fact, I mentioned this compound while discussing magnetism, is lanthanum copper oxide. So here you see a picture of the structure of lanthanum copper oxide. So these red atoms are oxygen, the blue small ones that you see here and here are copper atoms, and the green ones are lanthanum. So you see there are these corner sharing copper oxide CuO6 octahedra that span. So this compound has a tetragonal structure. So you have A, B, and C directions, and C lattice constant is larger. And in the AB plane, you have this series of copper oxide octahedra. So this is one plane, so to say, in containing copper oxide octahedra. Then you have some lanthanum atoms, and this would form another layer of copper oxide octahedra. And then this is another layer of copper oxide octahedra, and so on. So this compound has a layered structure. I'm spending some time on this because I want to contrast this to what we are going to discuss for conventional superconductors, and this will also connect to what we have studied in magnetism. Okay, so the essential building element, firstly, the properties of this compound or this class of compounds are very different. So they are anisotropic in the sense that, for example, if you measure conductivity, the conductivity in the AB plane would be very different from the conductivity along the C direction. And it is also believed that it's not just this, normal state physics, but also the superconductivity in these compounds essentially happens in the copper oxide planes. So here is the structure. As I said, the essential feature is this copper oxide octahedra. Okay, copper sitting at the center. Now, when you have a transition metal, and this is a structural unit that appears in many such oxide or similar compounds involving transition metal atoms. So you have a copper atom sitting at the center of this octahedron, and the formal valence states of the elements in this compound are the following. So lanthanum is in +3 state, copper is in +2 state, and oxygen is in -2 state. So if you add up, so this would be 6 + 2, 8, and 4 oxygens, so that would be -8, and you have a neutral species. All right, so so essential thing is that copper is in +2 state, okay? And so let me see. Okay, so copper has electron configuration 3d10 4s1. Now, if you take it to +2 state, this electron is gone, and one of these electrons is gone. So copper is in 3d9 state in +2. So copper +2 is in 3d9 electron configuration. So there are 9 electrons on the d orbitals of copper. Now, when you consider an isolated copper atom, the d orbitals, or in any isolated atom, the d orbitals, all the 5 d orbitals are degenerate. We have learned that. But when you place this atom at the middle of this octahedron, now the potential that the electrons experience is not spherically symmetric anymore. And because the potential is not spherically symmetric, there is no reason why all the ML states corresponding to a particular L value have to be degenerate. In fact, in general, they are not degenerate. So this is called a crystal field effect. You may have encountered this somewhere. So in this particular case of an octahedron, when you have anions sitting at the corners of an octahedron, you can also look at an octahedron as, there's a square in the plane, and then there are these two apical oxygens. Okay, and in a perfect octahedron, all oxygen-oxygen distances are the same. So I have anions sitting at the corners or vertices of the octahedron, and the copper atom sitting at the middle. And therefore, the electrons on the copper atom do not experience a spherically symmetric potential. So therefore, the degeneracy of the d orbitals can in general be lifted. And in this particular environment, there is a definite way in which the degeneracy is lifted. So let me try to share this. Let's see how it goes. Okay. So what I'm saying is, in an isolated atom, you have these 5-fold degenerate 3d orbitals, and in an octahedral crystal field, this
reposition and focus the screen.
Okay, in an isolated atom, you have 5-fold degenerate 3d orbitals, and in the octahedral crystal field, these split into two sort of groups. And don't worry about these terms. These terms come from group theory, and I don't know if you have done this, but if you simply look at the character table of the OH point group, you will find this. So there are 3 orbitals here, there are 2 orbitals here. Now I have 9 d electrons. So because this is lower, I can put 6 electrons here, 3 up and 3 down. So these orbitals would be completely occupied. Then I'm left with how many? 3 more. So one of these will have 2, the other one will have 1. So finally, I'm left with one of the Eg orbitals with 1 electron, although in principle, one can put, 2 electrons there. So there is a half-filled situation. So when you have such situations, you have an additional effect, which is called just get familiar with the name. I'm not going into any detail of Jahn-Teller effect at all here. But so the point to note is that one of the Eg orbitals is half-filled, and so there is a Jahn-Teller effect, which one of the consequences of the Jahn-Teller effect can be is that there is a distortion in the perfect symmetry of the octahedron. So the octahedron distorts slightly, which lifts degeneracy further. So this can be further split into this maybe a small splitting into 2 levels. Okay. So finally, what we have, the outermost orbital is this one. So this is completely occupied. and that is filled with 1 electron. So if you look at we'll go back to that picture. So if you look at the structure of copper oxygen plane, this is how it looks. Sorry. And so on. So there is an oxygen atom in between two copper atoms, and the coupling between the spins on the copper atoms is mediated by the oxygen atom, the oxygen p orbital. And this type of exchange interaction is what is called super exchange, which I did not discuss in course of magnetism. So let's not worry about the details of that, but the fact remains that these spins, this outermost electron spin on successive copper atoms are coupled via this intervening oxygen atom. So this is a super exchange, and that super exchange happens to be antiferromagnetic. So there is an antiferromagnetic super exchange coupling these copper spins, and so if I forget about the sort of atomic structure of it, this situation can be simply represented by a single band Hubbard model. You know, whatever, I mean, we had written this Hamiltonian before. So here is one example of a real material which you can describe by a single band Hubbard model. And in fact, this lanthanum copper oxide, this material happens to be a Mott insulator and an antiferromagnet. Happens to be a Mott insulating antiferromagnet with some nail temperature. I forget the value now, but reasonably large. And as you dope this with strontium, beyond a certain doping, below a certain temperature, which is doping dependent, you get this superconducting phase with a transition temperature that is somewhere around 35 Kelvin. Okay, so discovery of superconductor. So earlier, I mean, the superconductivity was discovered in a large number of metals, and it was sort of believed that if you can satisfy certain conditions, most metals, when cooled below its characteristic temperature, would become superconductor. But discovery of superconductivity in this compound, which is a well-known insulator, was quite a surprise. And soon it was, then people realized that the ground state of the parent material can be well described by this single band Hubbard model. There was a hope that superconductivity in this material could also be understood at a qualitative level using the same model, the single band Hubbard model. In fact, the single band Hubbard model, as we move away from half filling, by the way, the parent compound, because in the outermost orbital you have 1 electron, is a half filled situation for the Hubbard model. Now, as you start doping strontium in the material, you introduce holes. So it's like you are taking away electrons. So you are moving away from half filling. So when you move away from half filling in a Hubbard model, you get to what is called the TJ model. So it was hoped that this Hubbard model or its variant, the TJ model, would allow us to describe superconductivity at a qualitative level in these compounds. But that hope has, not turned into reality as yet, and we do not have any understanding of the mechanism of superconductivity in these materials as yet. But I just wanted to tell you this because you should at least keep in mind that the mechanism of superconductivity we are going to discuss does not apply to these class of materials and some other materials that I'll show you in a minute. Okay, so let's stop that for now. Yeah, there is some bit of information. So superconductivity, as I said, was discovered in 1911. So mercury was the material in which superconductivity was first observed, and soon lead and some other metals. And this is the curve that sort of represents the conventional materials, the conventional superconductors, and MgB2, which was discovered, early this century, 2001 or something. Yeah, 2001, I think. 1 or 2, whatever, around that time. So this shows pretty large transition temperature, larger than, in fact, this lanthanum strontium copper oxide. What is this? Yeah, lanthanum strontium copper oxide, which is around 35 or 38 Kelvin. But nevertheless, it turns out that the mechanism of superconductivity in MgB2 is the conventional one. So there's nothing surprising in terms of basic physics in its superconductivity. Whereas these are the compounds, the copper oxide family of compounds, which show pretty large Tc. In fact, when under pressure, this mercury compound is somewhere around 170 Kelvin or so. So these are the so-called high temperature superconductors. And as I said, we don't understand the mechanism in these materials at all. Then more recently, this century, there was a class of compounds called pnictides. So this, you see arsenic compounds, there should be some phosphorus, yeah, this phosphorus compounds, LaOFeP. So this group of elements, nitrogen, phosphorus, arsenic, these are called pnictogens. And so these compounds containing these elements are called pnictides. And superconductivity was discovered in this family of compounds containing pnictogen elements. And they also show pretty large Tc, up to 100 Kelvin or so. But the mechanism in these are also not quite understood. So that's the sort of picture till 2015. Now, so we leave it at that and get to the phenomenology of superconductors. So as we started by discussing that superconductivity means perfect conductivity. The resistivity goes to 0. So here is the experimental result from Kamerlingh Onus's own publication. So he was measuring DC resistivity of mercury, and as you see, as the temperature goes down to about 4.2 Kelvin, the resistivity vanishes completely, and there is no measurable resistivity. So this was called superconductivity. So that's the sort of defining feature of superconductivity. But as we'll soon discover, that's not all. So what superconductivity suggests is that there should be persistent current. So if you are able to set up a supercurrent in a system, I mean, supercurrent is something which is different from normal current carried by electrons. Then what happens? That's the question. Now, you see how, let us see how the resistivity of metals vary as a function of temperature. So a non-superconducting metal, I mean, I talked about this briefly. We did not get into the details that at low temperatures, the metallic resistivity of metals vary as T to the 5. So the general expression would be rho naught plus some constant times T to the 5. So this T to the 5 factor comes because of scattering from phonons. So when you go to T equal to 0, that term is not important, but then you still have a finite resistivity, and this is because you always have some defects in a material. So you can never have a macroscopic material which is perfectly crystalline. So that is rho naught. But when you have a superconductor, this is how its resistivity behaves. In the normal state, it shows this T to the 5 behavior, but then it abruptly goes to 0. And when it goes to 0, now in that situation, if you are able to set up a current, there is no scattering mechanism, right? So this rho naught plus B T to the 5 form appears because there is scattering of electrons from defects, which gives rise to rho naught, and then from phonons, which gives rise to this T to the 5 factor. Now, no resistance means there is no scattering mechanism. There's nothing that scatters that whatever the current carrying units are in the material. So therefore, if you are able to set up such a current, it should go on without decay because there are no scatterings. In fact, what has been observed is that, I mean, this is also old story. I can't tell you more recent experiments, but old in the sense, maybe 10, 15 years old. So if you set up a supercurrent, it can go on for years. I mean, people have measured for at least a year, a couple of years, that there is hardly any decay of the current. And whatever little decay they could detect in the current suggests that the lower limit for complete decay of the current, or the time scale, if you wish, for decay of the supercurrent would be at least 10 to the 5 years. And this is a statement that you will find in Michael Tinkham's textbook, is that under certain circumstances, now I don't know exactly what circumstances he's talking about, maybe very clean samples or no magnetic fields, blah, 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 I don't know exactly what. This time scales can be as large as 10 to the 10 to the 10 years, which is eternity for all practical purposes. So, that's how dramatic this effect is. Then let us look at the magnetic properties. So as you said, superconductors are perfect diamagnets. So what is a diamagnet? It opposes whatever external field you apply. So if you apply an external field to a superconductor, it completely expels magnetic field from inside. So basically the magnetic induction inside the superconductor is 0. It's exactly 0 in the superconducting state. That's why it's called a perfect diamagnet. So what I would like to emphasize is that this magnetic field is expelled from the interior of the superconductor. So you have a bulk material. Here we are talking of bulk materials. We are not talking about very thin materials, thin films, and so on. They have their own complications. The ideas remain the same, but one has to worry about some complications. So we are talking of bulk material. So in the bulk of the superconductor, the interior of the superconductor, the magnetic field is 0. The induction is 0. Okay. So in other words, it sets up an opposing field so that the net effect is 0. That's why it's called a perfect diamagnet. And one of the dramatic effects of this perfect diamagnetism is what is this levitation. And this effect of expulsion of magnetic field is called Meissner effect. But then suppose you have a superconductor and you start increasing the magnetic field. You have put an external magnetic field. When it is small, the field is completely expelled from inside the material. But then you start increasing the strength of the magnetic field. What happens? Turns out that, well, exactly what happens depends on the type of the material and the type of superconductivity it undergoes. One have two types of superconductors. So let me go to the board. Let's see. So there are two types of superconductors. Type 1. In these, what happens is, as you have increased the magnetic field beyond a certain critical field, the whole sample becomes normal. Normal meaning not superconducting. And that critical field is, of course, temperature dependent. So if you plot the critical field as a function of temperature, you will get a curve that roughly looks like this. So this is Tc. Beyond Tc, of course, there is no superconducting phase. Here it is superconductor. So at any temperature, if the magnetic field happens to be lower than this value, smaller than this value, then you have the superconducting phase is retained. The magnetic field is expelled from inside the material. But once you go beyond this, abruptly, the entire sample becomes normal. There's no superconductivity anymore. These are called type 1 superconductors. Then there are other superconductors in which, as you increase the magnetic field, there is a lower critical. So this is called the critical field. Then there are these type 2 superconductors in which below this lower critical field, which is called Hc1, the field is completely expelled. Then you have an upper critical field, Hc2, above which you destroy superconductivity completely, and the system goes to the normal state, non-superconducting state. But then what happens in between Hc1 and Hc2? What happens is that field lines, magnetic field lines, do enter the sample. So suppose I have a sample which is a block, something like this. And then I'm applying a magnetic field in this direction. So below Hc1, everything is expelled. As I cross Hc1, magnetic fields enter the sample, but as discrete flux lines. As I increase the magnetic field, as the magnetic field keeps increasing, more and more flux lines, and this flux in each of these regions, the flux has to be quantized, which we'll get to later on. So flux enters this sample in discrete quanta. So this is one flux quantum, that is another flux quantum, and so on. And what is interesting is that then, of course, as you keep increasing this, more and more flux lines enter, and beyond Hc2, the whole sample becomes non-superconducting. But in this intermediate phase between Hc1 and Hc2, these flux lines have their own very interesting physics. What happens is that they interact with each other. They interact with each other and they repel each other. And as a result, at low temperatures, these flux lines, so I have these flux lines entering the sample. If I look at a cross section perpendicular to the flux lines, for example, if I look at the surface over there, the flux lines at low temperatures arrange themselves in a definite pattern. In fact, they form a triangular lattice. And then as you increase, keeping the magnetic field fixed, which means keeping the number of flux lines fixed, if you start increasing the temperature, then these flux lines, of course, start moving. In fact, remember, so when we are talking of a lattice, it's a different type of lattice in the sense that these are not discrete points. In a cross section, of course, I see discrete points, but actually these are extended objects. Okay, these are flux lines running through the entire length of the sample in that direction. So they start wiggling about as you increase the temperature, and then beyond a certain temperature, they actually melt. That lattice melts. The lattice of flux lines melts, and they undergo a solid liquid transition, but it's a different kind of liquid in the sense that these are not liquids of point objects, these are liquids of strings and so on. So there's a fascinating physics associated with these flux lines, but that's not something we will get into. I'll just show you a picture to visually convince you that these do form lattice. So let me see if we can find that. Here. This is at the surface of some type 2 superconductor at a magnetic field which is between Hc1 and Hc2. And then what is done in these experiments is these are called this is probably a better picture. Let me see. These are not okay. Let me show this picture anyway. So here they have measured something else, but actually what one does is, and quite often what is done is that you just sprinkle iron filings on the surface of the superconductor. And what the iron, fine dust of iron particles, what they would do is they will of course go and sit where the flux lines are, where the magnetic field is. They wouldn't like to sit where there is no magnetic field, and you find that they form this kind of pattern. And if you look very carefully, you will find that they form a triangular lattice. For example, this is a hexagon with this point at the center, and so on. So this is the kind of triangular lattice one is talking about. They form triangular lattice, and then as you keep increasing the temperature, this lattice melts. But remember, these form a lattice of lines, not lattice of points. Okay, so that's about flux line lattice. Type 2 superconductors and lower and upper critical fields. See, if one were to draw how the magnetic induction varies inside the sample, in type 1 versus type 2 superconductors. Okay, can you see this or is it not clear enough?
It's clear, sir.
I don't know why it. Sorry, just got disturbed. All right, so this is the equation we had arrived at. Now, what was tau? Tau was basically the average time between collisions, so to say, or you remember this relaxation time. Now, because there is no scattering event in superconductors when there is a supercurrent flowing, so tau in that sense is infinity. So I can neglect this first term, and this is a very crude argument, but it will serve our purpose for now. I mean, one can make it more subtle and see that there are limitations to these arguments. If you are interested, you can read so for this topic, I'm following two books, combining two books. One is Ashcroft and Marmin, the other is Tinkham. Now, Tinkham is a detailed sort of textbook on superconductivity itself. Now, I cannot, of course, discuss all the details that are contained in that book, but if you're interested, you can always refer to that. On the other hand, Ashcroft and Marmin is in some places too elementary, so I have to combine these two. Okay, anyway, so this is the equation that we write, and then you assume that there's a total electron density n, and while considering normal current, I mean, so far we have only considered normal current. So if you multiply this velocity by n and e, the electron charge, you get the current density. So here what one assumes is that a fraction of this, a part of this, carries the supercurrent. So this is the density of electrons responsible for the supercurrent. So then, if I multiply this, so VA should be the velocity of the electrons responsible for the supercurrent. I'll get the supercurrent density. So using these here, what I'll get is M or yeah, that's okay. So then all right. Now we have these relations, and if you combine these two relations, you will get so if I take the curl here, I'll take the curl on this side. So I'll get something involving curl of Js. So what we'll get is so this will give you curl of E is in this is in squared. All right. So then I can combine these two. Okay, both are curled E, so I can equate these two, and from that what I'll get is actually I'm doing this inside the superconductor, so I'll actually replace this by B, this ddt, yeah. So this is equal to 0. So I'll just write it in a slightly different form. Okay. And then I have also the Maxwell's equation, curl B for the supercurrents. Okay. Now, now what is happening in a superconductor is that as you apply the magnetic field, that is expelled from inside the material. So there has to be an opposing magnetic field that is being set up inside the material. Now, how does that happen? The way it happens is that, suppose I'm looking at a cross section. For simplicity, I'm taking a cylindrical shaped wire, which is running along this direction. And suppose the magnetic field is applied in this direction, which is expelled from inside the material. There is no magnetic field here. So there has to be something which creates an opposing magnetic field. And that something is that a supercurrent is set up in an appropriate direction at the surface of the material, which creates this opposing field that cancels out the external field. Now, any magnetic field that sets up a supercurrent will trivially satisfy this, any static magnetic field, okay? Because, whatever this is, there's a magnetic field which sets up a supercurrent, but then you are taking, if these are static objects, you are taking time derivative of that. So any B and the corresponding Js, any external field H and the corresponding Js would sort of trivially satisfy that relation. So that's not what exactly would describe the situation of superconductors, because we specifically want the situation where the B field inside the material is 0. So we have to arrive at that solution, even in a static case. So we want the B equal to 0 solution. So this is a work by London and London, two brothers. So what they suggested is that we look at the special situation where, so this would be satisfied for any perfect conductor. Okay. On the other hand, for superconductors, what the Londons suggested is that we look at this specific subset of solutions where this is identically 0. So this is not just time independent, this is exactly 0. Now, if that happens, then you take a curl on both sides. So this would give you del square B minus del square B. This would cancel. I mean, there is a minus sign. No, there is no. So in place of this, I'll place this, and there is 4 pi. So we'll arrive at this equation. Okay, you just write this in terms of whatever divergence of B and del square B. In place of this, you substitute this, and then this minus sign will go away, and you have this. So then, so this is suppose written as like this. So let us now consider a particular geometry where I have a superconducting material. So this is my X direction. This is my Z direction. So this part is superconductor. This is out. So this part is my superconducting material. This is just say free space, and I've applied a magnetic field, external field in this direction. And I want a solution where this B would be 0 in this part. So then if you solve this, what you will get is that B as a function of X, Bz as a function of X would be B0 at the surface e to the minus X over lambda. So the B field would be exponentially suppressed as you go inside the material. So this is what happens at the surface. There is a length scale of lambda over which this field is screened out, and this lambda is called, so this is a very, very important length scale in superconductors, is called the penetration length or penetration depth, something like that. So this is the length scale over which the magnetic field is screened out starting from the surface. And in conventional superconductors, this length scale happens to be few hundred angstrom, 200 to 500 angstrom at low temperatures. All right. And similarly, if you write down the equation in terms of J, which I'll probably leave as an exercise for you, you will get a similar relation. And so basically that would tell you that the supercurrent would be set up within the length scale lambda starting from the surface, which screens out the external magnetic field. All right, so there's something more about free energies. Probably I'll get to that next time. So let me just get started with the basic discussion of BCS theory, and then we'll come back to this and complete it next time. Okay, so getting back to that first point, that even the tiniest attractive interaction between electrons can destabilize the Fermi sea. So how do we argue about that? So let us start with this Fermi sea, and then suppose we have two electrons that have attractive interaction between them. Okay. Now these two electrons are not part of this. So let's say we have two additional electrons that would be added to this Fermi sea, which have attractive interaction between them. So one is looking at a two electron problem in the background of this Fermi sea. Now there is some argument due to Bloch which suggests that when you have this, the total momentum equal to 0 state would have the lowest energy. So we'll consider a state in which, so firstly we are considering two electrons in the background of Fermi sea. They have attractive interaction. Third, total momentum equal to 0 is the ground state. So if one happens to be in some K momentum state, that's how those states are labeled. These are non-interacting electrons. So remember, the Fermi sea, of course, represents non-interacting electrons. There are these two electrons which have attractive interaction between them, but they don't interact with the electrons within the Fermi sea. So that's the problem one is studying here. So one electron has momentum K, the other has minus K. That's the situation we are considering. So the two electron wave function is written as, so we have to construct this two electron wave function of these two electrons. Okay. So let's write the spatial part of the wave function as simply write Kf. Where Gk, these are the weights with which plane wave states associated with momentum K and minus K contribute to this sum. So this is written as a sum over products of plane wave states, which are of course one particle states. And so the GKs are the corresponding weights. Now there is of course a spin part to it. And so this is how one can argue about it. So see, this is of the form so this can be viewed as having one part which is cos k dot R1 minus R2, the other part which is sine generally, the even part becomes the ground state. Here you can argue by saying that, see, this has high probability, or that is mod psi square would be large when when R1 is equal to R2, and that should be your ground state because there is an attractive interaction between the two electrons. That's the case we are considering. So this is, this can be argued to be the ground state wave function, not that one. And so with cos then, which is an even function, the spin part has to be odd, so it has to be a singlet. Okay, so that should be the ground state. So the bottom line of this argument is that singlet is expected to be the ground state. So one is spin up, the other is spin down. Okay, fine. Then what do we do with this? We have to put this wave function, or this form actually. We'll use this in the Schrodinger equation for these two electrons. So let me write that.
Why do you take cos? I didn't get
Cos, because cos has a higher amplitude when R1 is equal to R2. So the two electrons will have large probability of being close to each other, and that's a good thing because we are considering an attractive interaction. So therefore, it's likely that, or on general physical grounds, you can argue that state should have a lower energy compared to the sine state, which excludes R1 equal to R2. All right. So what is the two electron Schrodinger equation? And this capital E is the energy of the two electron state. So we'll write down the wave function we just wrote. And in fact, anticipating the kind of simple form for V that we will take subsequently, I'll just write this as VR1 minus R2. Okay, now you see this, from this will just give you k squared. I have not written the H square and M factors, understood. And there, so these two terms both will give you K squared, right? So therefore you get, with half, you get a 1 K squared factor. And times, okay. And then what we'll do is, we'll multiply by this. This is a volume, e to the minus, I believe. In fact, I'll write R1 minus R2 as R. So I multiply by this and then integrate. So from this second term, the first term will just give you, so if you multiply by some K primed, you'll get a K primed here. And then the second term will give you and then you have, I'm not writing, so K is greater than Kf because we have to add the 2 electrons at K vectors that are greater than Kf. So that's why this K greater than Kf here. And here I'll get so this will also produce a delta function. So only thing that is not a delta function is this part. So we'll write that as, so sorry, K prime square GK primed. So K prime square GK primed. And this thing I'll write as VK primed K. So this, and this with the integral is written as Vk. So it's just a Fourier transform of the potential V of R. And that is equal to E Gk primed. Now you interchange K and K prime just for the sake of, nicety. There's nothing else. Instead of making K the dummy index, I'll make K prime the dummy index and K the free index. And what is then K squared? Okay, K squared is just the energy of the K state for non-interacting particles. So that I'll call, or rather K squared by 2 would be the energy. So this will be twice epsilon K primed, where epsilon Ks are the energies of one particle states in the non-interacting system that constitute the Fermi C and so on. So if I rearrange these terms, so what I'll get is E minus twice So that's the equation I get, which in terms of these energies gives me the energy of the two particle state. Okay, this is this energy. So the point is, if I can find some G which gives me an energy E that is less than twice EF. Now try to understand this point, this argument clearly. If we can find a solution to this equation with energy which is less than twice EF. Why twice EF? Because the minimum energy I have to spend to add 2 electrons. What is the K at which I can add 2 electrons? It has to be Kf. It cannot go lower than Kf because all these states are occupied. So the minimum possible energy is twice EF, possibly higher than this. But if I am able to find a set of GKs which gives me a solution where this E, the energy, is less than twice EF, that would indicate that the Fermi sea is no longer a good description of the ground state, because I have found a state which has a lower energy for these 2 electrons. So that's the sort of argument that we will follow. Okay, so I think it's a good point to stop today, and we'll take it up from here next time, and we'll look at some other points. And